Okay, let's find our seats, everyone. So our next speaker is Lukas, the Institute of Physics of the Czech Academy of Sciences. I think what CAS is. A question that we've been asking some of our speakers, did you first encounter the field as MicroED, 3D ED, and does it really matter because we're all going to go to 40 STEM?
Can you repeat the question, please?
Did you first hear about us through MicroED, 3D ED, in terms of this field that we're talking about, or does it really matter because science only really matters?
Oh yeah, well, that's a good question. Well, hello everybody. Warm greetings from Prague, from evening Prague. Well, I first encountered the field when it was called ADT, and I went through all the changes of name and proposals of various names, and for me it is I think the 3D ED is the preferred abbreviation, but well, MicroED is just the same thing, and I hope that we can get over the let's say little fight that we had on the topic. Of course, in the end, it's the science that matters. So it is important that we know what we are talking about, and as long as we understand that MicroED and 3D is the same thing, and we understand where it comes from, it doesn't really matter that much. Okay, well, so my task is to give you a little overview of the whole procedure that's required to get from the experiment to the structure on the screen. So of course that's a vast topic, so it will be rather a quick overview of the basic steps, and I will try to focus on the specifics of the 3D ED workflow. I will relate often to how things are done in X-ray diffraction. So for those of you who are familiar with X-ray diffraction, you'll get the differences. But if you're not, don't worry. It will still, I believe, it will still be comprehensible. So, well, I guess by now you are familiar with the experiment, so you know what a 3D or MicroED experiment is about. So this is a little animation showing the basic idea. We take a crystal, we rotate the crystal, collect the diffraction patterns. We end up with a collection of diffraction patterns associated with crystal orientation. And then the first step in the whole procedure leading to the structure is data processing, which provides us lattice parameters, some idea about the symmetry, and of course extraction of, if possible, accurate intensities that will then serve in the next stage for the structure solution and kinematical or dynamical refinement of the structure model. So let's first focus on the data processing step. And here I should point out that there are various data collection strategies. The first here on the top left is the original one that used to be called ADT, automated diffraction tomography, and that was a collection of static frames without any continuous rotation or precision. This is not optimal because there are big gaps in reciprocal space that are not covered in the experiment. So historically, the next one was precision assisted 3D ED or PEDT, precision electron diffraction tomography, where the gaps were filled by using precision electron diffraction, which is a technique where the beam is rotating around an axis on a small cone, typically opening angle of 1 degree. And then the intensities were already integrated during the experiment. That is still used. It still is a useful technique, but by now the most common technique is what's called CRED, continuous rotational electron diffraction, or also MicroED. Most people, when they say MicroED, they mean this technique when the crystal is continuously rotated around an axis, and then the diffracted intensities are collected on a set of diffraction frame, where each frame corresponds to a certain wedge of reciprocal space. Then there is also, say, an emerging technique, which is called serial ED, serial electron diffraction, where each crystal gives only one or a small number of diffraction patterns, and then just like in serial X-ray diffraction, the data are combined from many crystals. It can be a few thousand crystals into one data set, and the structure is so. But I will focus mostly on the continuous rotation, but also on precision techniques. There are no big differences in the data processing between these two. So when it comes to the software, there is a lot of software available in the field. They can be divided roughly into two main directions. One are X-ray based programs that are adapted to electron diffraction. Among the most widely used, it's the XDS and also Dials by David Rothman. There is Chrysalis Pro from Rigaku, and also Apex from Bruker is used frequently. So all these programs can be used. And then there are dedicated programs developed directly, specifically for 3D ED. That's PETS2 that we developed in Prague. That's ADT3D in Mainz. There's also a RED-P program in Stockholm, although I don't think it is being actively developed these days. So there is a lot of choice, and all these programs essentially share the same philosophy, the same idea that I will really briefly summarize here. So first, we need to extract the positions of reflections in all the reflection patterns. Then we have to construct a 3D reciprocal space out of these two-dimensional refraction patterns. Then we have to find the unit cell parameters. And optionally, but it's quite an important thing to do, we may want to correct various experimental distortions, geometry issues, and so on. And then finally, once all the geometry is correctly in place, we can extract the diffracted intensities and obtain a list of reflection indices and their diffracted intensities and their standard uncertainties, which is the input to the next stage to the structure solution. So step by step, peak hunting. When you get the diffraction pattern, it contains a number of reflections, and the task of peak hunting is to find the positions of the strongest reflections on the patterns. In 3D ED, part of the problem is that the center of the refraction pattern may not be stable. It may differ from experiment to experiment, but even from diffraction pattern to diffraction pattern in one experiment. So one of the challenges of this stage of data processing is to be able to locate the diffraction pattern center, which is almost trivial when the transmitted beam is contained in the diffraction pattern, like in this case. But if you have a pattern like this with a beam stop that covers the center, it may be a bit of a challenge. And the second challenge is to find the projection of the rotation axis. On X-ray diffractometers, this is mechanically stable. The rotation axis is always the same and can be calibrated. Essentially, it's not moved. In 3D ED, the position of the rotation axis may depend on the settings of the microscope, and it may change from experiment to experiment. So it's important to get the position of the rotation axis or the tilt axis projection correctly. This can be achieved quite elegantly using the cylindrical projection of the reciprocal space, which you can see here. So you basically take the diffraction space already projected or reconstructed in 3D and project it on a cylinder that's wrapped around the reciprocal space, the cloud of points. And if the points form a lattice, they project in this nice array of spots that form these nice sinusoidal lines. If you are off, like in this bottom image, that's 20 degrees off, then you see that the cylindrical projection is less sharp, and you can clearly see the result. So that's the basis of the refinement of the tilt axis. It can be done even without knowing anything else about the data. So once the tilt axis is known, we can reconstruct the three-dimensional reciprocal space from the two-dimensional positions, because each diffraction pattern can be understood as a two-dimensional section through the three-dimensional reciprocal space. And because we know the position angle of the crystal for every diffraction pattern, we can combine all these diffraction patterns into a three-dimensional picture that you see. One view of that three-dimensional distribution you can see here on the right side. Because we can't tilt the sample plus minus 90 degrees, well, in principle, maybe we even could in some microscopes, but because of the support of the crystal, the crystal becomes or gets shaded sooner or later, so it is not practically possible. There is always a missing wedge, so-called missing wedge, the area which we cannot reach on a single crystal in a typical instrument. That's one of the complications we encounter with 3D data, and this missing wedge can either be filled by symmetry. If the crystal has higher symmetry, then symmetry related areas to the missing wedge might be measured, or we need to combine more crystals into a single data set to fill this missing wedge. Nevertheless, for determination of the unit cell parameters, this missing wedge is not so important. It's quite clear that from such a cloud of points, it's relatively straightforward to find the unit cell of the reciprocal space that describes such set of points. This can be done either automatically by indexing algorithms or even manually, just by rotating this cloud and indicating what are the special directions in reciprocal space. So whichever option we choose, we get some starting unit cell parameters that need to be refined. They need to be optimized, fitted to best match the data. And at this moment, there are complications that we need to deal with, and they are of three types. So to say, you see here the diagram. There are optical distortions in essentially every electron microscope that distort the image. There are mechanical instabilities, both of the goniometer, but also of the crystal. The crystal may be rotating during the data collection, for example, due to warming up and changing its volume. But also, if you happen to change the position on the crystal during the experiment, you might be illuminating a different position during the experiment, and then these different positions might have slightly different orientation due to crystal bending. And then there is the third aspect, and that is radiation damage. Radiation damage, as we will see, can and does have impact on lattice parameters. So all these three aspects have impact on the accuracy of the lattice parameters, and as a result, typically the lattice parameters obtained from 3D ED are less accurate than lattice parameters from X-ray diffraction, and even less accurate than lattice parameters from powder diffraction. Here you can see some effect of these distortions. On the left, this is an image, a diffraction pattern with an overlay of predicted positions in case when distortions are not properly corrected for. This is quite an extreme case to make it visible clearly on the screen, but still you can see that the circles are just away from the actual positions. And of course, in this case, it's not possible to extract the intensities correctly. So this can happen when the distortions are not correctly accounted for. The plot here shows the corrections of the orientation of the crystal. There are 3 positional angles that describe the orientation of every diffraction frame. And you can see that there are corrections in this case, say at about half a degree. So the vertical scale is in degrees. So for example, the green line, which is the beta tilt, changes from something like 0.05 to minus 0.4, so almost half a degree. These are small corrections. Half a degree, you would barely see it, but it has an important impact on the accuracy of the lattice parameters. And finally, the radiation damage. This is again quite an extreme but not completely unusual case of the effect of radiation damage. This is a large crystal that was measured in 3 batches, and during the tilt, the beam was shifted 4 times on different parts of the crystal. And this curve shows the magnification correction, so basically the scale or overall scale of the lattice parameters. And you can see how this magnification correction goes down as the crystal is illuminated. And then as we move to a new position of the crystal, it goes up again, and then down and up and down. And the magnification correction going down means that the lattice parameters are increasing. So the crystal is swelling and this is a typical effect of radiation damage. And again, this is in percent. So the total error or change in the dimensions of the unit cell can be almost 1% or more than 0.5%, simply as a result of radiation damage. So all this has to be taken into account and kept in mind when you interpret lattice parameters from 3D. So as I said, they tend to be have lower accuracy, but there are ways to correct for this, and there are a few options that we can exploit. The first and the most straightforward is just the 3-dimensional refinement of cell parameters against the positions of reflections in 3D space. This is the standard way, but the most prone to all these errors in crystal orientations and also in optical distortions. Then there is a 1D refinement or refinement from D spacings. If you are familiar with powder diffraction, then that's exactly the same principle as refinement from powder diffraction data. There only D spacings are known, and still the unit cell parameters can be refined. So here we can do the same thing, and this is less prone to some of the orientation errors, but not to the optical distortions. Then another useful option is to refine against reflection positions on the diffraction patterns, and this refinement allows the refinement of optical distortions. So you can refine together the lattice and the deformations due to the optics of the microscope, and that permits, under favorable circumstances, to decouple these effects, the lattice parameters, from the distortions, and get a decent result. So here is a quick one example. This is a monoclinic cell, and you see that with the standard refinement, the alpha angle is more than 0.5 degree off. Now, after refining the optical distortions, suddenly this is not 0.5 degree off anymore. It's almost 90. This is almost exactly 90. And then after refining the crystal orientations, in this case, there was very little change, but this angle becomes even closer to 90 degrees. So here we are within, let's say, 0.07 degrees away from a perfect 90 degrees angle. Okay, so once we find the unit cell parameters, we can go back to the diffraction patterns, and now we can predict where we expect reflections to be, and then we need to extract the intensities from the diffraction patterns. It's important to predict all the positions, including the positions where there are no peaks. So we are not only looking at where we see peaks, we are also looking where there are no peaks, because the information that the intensity of the reflection at some positions is very low is also a useful structural information. So we extract intensities from all positions, typically within certain resolution. And then there are two basic approaches to this task. We need to extract the complete intensity, all the intensity that was diffracted for one reflection on all the reflection patterns. Typically, reflection is found on more than one diffraction pattern. It has certain size in reciprocal space. And this is illustrated here on these small cutouts here on the top. So each of these squares is the same reflection occurring on consecutive diffraction patterns. You can see how the intensity goes up, and then it fades down a little bit, then goes up again, and then disappears. This is a typical pattern for data collected with precession electron diffraction geometry. So in that case, the profile looks like this. It has two maxima. That's why we call it a camel. In case of continuous rotation data, there is no double maximum. There is just an increase of the intensity and then decrease again. And so we can either extract the intensity on each of these frames and then combine these intensities together in next step. That's what I call 2+ 1 dimensional approach. That's what happens in PETs. Or you can directly fit all the frames together in, and you can fit a 3-dimensional profile to all these intensities together. And that's a 3D approach that is used by XDS, also, as far as I know, by Dials and Chrysalis Pro. But basically, the idea is always the same. Let's try to extract as accurately as possible the total intensity diffracted into each reflection. So as a result, in the end, what we as users are most interested in is some statistics that tells us how good the data are and how good they can be, how well they can be used for extracting the information. And that is typically summarized in a table like this, which splits the data into a number of resolution shells, from the lowest resolution all the way up to the highest resolution that we see in the data. And that this table contains like a range of statistics. I would point out the completeness, which is important. In this case, the completeness is about 70%, which is not great, but sometimes we just can't do better than that. And even from a 70% complete data, it is often possible to solve the structure and even to refine it to reasonably well. But in general, high completeness is desirable. The intensity over sigma, which tells us how strong the data are, and then Rint and CC1/2, which are some statistical measures of how internally consistent the data are. These numbers tend to be higher for Rint and lower for CC1/2 than the typical X-ray diffraction data. So for X-ray data, we would expect here to have something like, well, let's say less than 5%. But due to the dynamical diffraction effects, to which we will come later. In electron diffraction, the internal consistency of intensities is worse than for X-rays. So an R int of 13%, like in this case, is actually a very nice number. So at this point, we have a list of intensities, and there are actually two different ways or two different types of intensity list, depending on what we want to do with the data in the next step. One option is to assume kinematical diffraction. So assume that the intensity is proportional to the structure factor amplitude squared. And in this approximation, so with this approximation, we can use the data for the standard X-ray-like processing, structure solution, and refinement. If this is the goal, then the processing can involve like averaging the reflections, scaling them together, and doing all the nice and cute tricks that have been developed already for X-ray diffraction data. On the other hand, we may want to go to be more accurate than this kinematical approximation, because we know that that approximation is only really coarsely, roughly valid for electron diffraction data. Electron diffraction is dynamical. We'll come to that in a second. So if we want to use to do a proper or more accurate refinement, we may want to go for dynamical refinement, which is available in the software IANA 2020, and recently also for the users of Synergy ED and Chrysalis Pro. It's also available in OLEX 2. And that requires a slightly different extraction of intensities, and most importantly, saving of some additional information like the orientation matrix and definition or more definition of how the data were recorded, because the dynamical intensities require this information for, or the dynamical diffraction theory needs that information to be able to correctly calculate the intensities, the dynamical intensities. So once we extract the intensities, the next step, typical next step in the data processing pipeline is the symmetry determination, or at least an estimation of that. That can be easy, but it can be also complicated. I will not focus on the easy part. If it is easy, then it's usually an automatic procedure. But I want to point out a few problems that can occur in this step. So first, I mentioned already inaccurate lattice parameters, which may induce some ambiguities even in the determination of the crystal system. Is the crystal orthorhombic or is it monoclinic? Is half a degree deviation from 90 degrees a significant or not, significant deviation or not? So if there is an ambiguity of this type, then the possible solution is to get external information about the lattice parameters. Like if you have enough material, you can collect the powder pattern and refine the unit cell on the powder pattern, or you can guess the crystal system from systematic absences. Or, as I said, you can apply corrections for optical distortions of the microscope, and that can improve the accuracy of the lattice parameters. Also, the R-int value, so the internal consistency of symmetry equivalents, may be high, and it might not be really straightforward to even determine the Lave class of the crystal. And here, I would recommend ideally always checking reciprocal space sections, the special sections through reciprocal space, and they are often useful in verifying the symmetry. This is one example, one quite subtle example. This is a nickel titanium alloy, and it was reported to be cubic in the literature. So we got this material and measured it, and we indeed got a cell that was quite cubic, although the angles were somewhat suspiciously off 90 degrees. But this is something that is not really unheard of in 3D-ED. But if you look at the section through reciprocal space, so this is the, let's say, the HK0 section. If you look carefully, there are important differences in some reflections. So if this was cubic, then there would be an axis, a symmetry axis here. So the left part and the right part would have to be the same. But if you look carefully, you see that it is not the case. This reflection is strong, this is absent. This is very weak, this is rather strong. So by looking at these differences, there are more of them, but this is the most visible part. You can guess or verify that this is actually not a cubic structure, but it has a lower symmetry. And indeed, if you transform them into rhombohedral setting, then it's clear that now the angles are perfectly what they should be. There is no deviation of 1 degree. And the subsequent analysis really showed that this structure is rhombohedral and not cubic. So the dynamical effects also generate intensity of kinematically forbidden reflections. So the glide and screw systematic absences are often violated. And here again, the reciprocal space sections help. If you know what to look for, it will give you a more reliable guess whether a systematic absence is there or not. Here, an example again. This is a tetragonal structure, and if you look at the statistics for various possible tetragonal space groups, there is a space group P4 over MBM, which has, out of 200 possibly extinct reflections, there are 34 observed ones. So actually quite a decent number of all possible systematic absences is observed. So normally you would say this cannot be the correct space group because there are too many violations of systematic absences. But if you look at the section through reciprocal space, so this is the H0L section, you can see that there are violations of systematic absences. So like all these reflections that I'm showing here, all these, they should be absent. But if we go away from the center of the diffraction pattern, we can see that the systematic absences are actually quite well there. So the reflections are missing. They occur only close to the origin of the reciprocal space. So actually this material does have a space group P4 over MBM, and all these additional reflections that shouldn't be there are the result of dynamical diffraction. So this is really something that you need to be careful, and unfortunately I've seen more than once incorrect interpretation of symmetry from 3D data, claiming that the space group cannot be this or that because of systematic absence violation, and very often it turns out to be a false estimation. I should point out that this is a more serious problem for inorganic structures than for organics. But even in organic structures, sometimes the systematic absences can be surprisingly strongly violated. So to summarize the symmetry determination part, I just say this is the step where you can play the role of the crystallographer. This is the moment where a good crystallographer stops just clicking buttons and uses their crystallographic knowledge to verify that the automatic procedures got the estimations right and potentially correct them. So once we get through this step, it's time for the magic, for structure solution, for getting from the list of intensities to a structure model. That's, of course, a wonderful topic, wonderful branch of crystallography, but let's be honest, nowadays, most people use the structure solution programs as a black box. Intensities come in, structure model comes out, and even though I I developed one of these programs, I completely understand that this is why this is the case. First, these programs are quite powerful, say that they just do the job without us needing to know how and why. And second, it is not really easy to understand and penetrate the techniques and be able to modify the settings of the programs to get a solution if the defaults fail. Luckily for us, the programs work really well, so it is usually not so difficult to get a structured solution. And if it is a problem, then the problem is very often on the side of data. The data need to be simply better. There are three programs that are commonly used for solving X-ray structures and 3D ED structures as well. There is SEER. This is a logo of SEER 11. I think there is now a SEER 2024. I'm not sure, but there are frequently new versions. Quite powerful program. There is Superflip that we developed first in Switzerland, and then now we maintain it in Prague, which is based on the charge flipping algorithm, also a dual space iterative algorithm, and of course the most widely used program, ShellXT, that is using also a dual space iterative algorithm that's called intrinsic phasing. These two programs have in common that they do not explicitly use the symmetry in the structure solution process. They find the symmetry, they solve the structure without considering the symmetry, and then they try to verify that the solution contains the symmetry. And that is very useful if you're not certain about the space group after the symmetry analysis step. Very often these programs can give you a hint that your estimation was wrong or correct, so they can validate your choice of symmetry. As I said, there's not much we can do if the solution fails, but still there are a few tricks I can recommend. First, check the refraction patterns and delete anything that doesn't look good. Very often at the beginning or typically at the end of the data collection, the diffraction patterns don't look good, and in general, it is better to exclude bad data than to put them in, even if you lose part of the completeness, for example. So that can help. My favorite trick, check the reconstructed density or electrostatic potential, not just the structure model. Quite often, the model does not look that great, but the reconstructed potential actually contains a solution. This is an example. Again, this is an inorganic structure, and if you would look only at the interpreted atom positions, they don't look very nice. It's barely recognizable that this is a real structure. But if you look at the maxima in the potential, you will see after some consideration that the structure is actually there. This is a part of an iron O6 octahedron. This is part of an arsenate tetrahedron. So basically the structure is there. It's only the interpretation that failed. And if the coverage is low, combining data sets from 2 or more, 5, even 10 or 20, if you have them, crystals can very often help. And finally, again, as I said, be careful about the symmetry. This is the output from Superflip that is estimating that the symmetry of the current solution is C, and then you can verify that against your guess from the diffraction data analysis. So, and then when we have a structure model, the next step is refinement. We need to refine the structure to get an as accurate structure model as possible. And here we come to the probably biggest difference between electron and X-ray diffraction data, and that is the validity or invalidity of the kinematical approximation. So for X-rays or for neutrons, in general, if a radiation has a very low scattering cross-section, then there is virtually no multiple scattering, and then it can be easily shown that the intensity is proportional to the structure factor amplitude squared. So the structure factor is the Fourier transform of the electron density or scattering density in the unit cell. So if this is valid, then we call it kinematical approximation, and then things are comparably easy. Unfortunately, for electrons, the kinematical approximation is valid only very, very roughly. And in fact, electrons interact with atoms so strongly that dynamical, so multiple scattering is unavoidable. Even in particles as small as 5-6 nanometers, there is a measurable amount of multiple scattering inside of these tiny particles. And if that is the case, then we need to use a dynamical theory of diffraction if we want to get the accurate results. In this picture here, this is a schematic illustration of why the multiple scattering occurs for strong interaction of electrons with matter. This is a diffraction pattern. This is a central peak, and these are the reflections with intensities that would say correspond to a kinematical case. But now, if the interaction is strong, then every diffracted reflection or every diffracted beam can act as a new primary beam that can diffract again. So if we pick one of these reflections, this one, it acts as a new primary beam, and it diffracts again. So suddenly you get an overlap of two diffraction patterns, each emanating from a different primary beam. And of course, this doesn't happen with only one reflection. It happens with all the reflections in the refraction pattern. So the result is some kind of a convolution of the refraction patterns over the whole diffraction pattern. So luckily, the theory is available. So in principle, it is not complicated to calculate the diffracted intensities in the dynamical case. Now, if we stick with the kinematical refinement for a moment, the advantage is that it is very simple. It uses the techniques that have been developed for X-rays, and so any X-ray structure refinement program can be used without any modification or with very small modification for electron diffraction. On the other hand, because of the poor validity of kinematical approximation, the results, the accuracy of the calculated intensities is poor. Therefore, also the match with the experimental intensities is poor. And the result, the most visible result, are high R factors. This is a table of about 200 structures solved by Robert Bicker, who was kind enough to provide me, give me this plot. It's a bit old already, but the situation has not changed since that time. So you see that the typical R factor for a kinematical refinement is something like 18, say between 15 and 25%. So for a small molecule X-ray diffraction, this would be a very poor result. But that's the price to pay for using this relatively poor approximation. But actually seeing how bad approximation it is, it gives surprisingly good results. You can solve the structures, you can refine the structures, to reasonable accuracy, especially if you are interested in molecular connectivity. So in basic outline of the structure, then the kinematical refinement is really fine. But the issues to keep in mind are that you may have significant errors on atomic positions, up to 0.2 angstroms, which is not a lot if you are only interested in connectivity, but of course it may be a lot for some more subtle details in the structure. The refinement is relatively insensitive to atomic numbers and occupancy. So it might be difficult to determine atomic species that are close to each other or even that occupy the same site. And you need to determine the relative occupancy of that site. Because the R values are high, there is no easy means of validating the structure. In X-ray diffraction, if you get an R factor down to 5 or 4%, there is still room for error in the structure, but you can be very, very confident that the basic outline of the structure is correct. With an R factor of 25%, there is a lot of room for hidden, even like fundamental errors in the structure. So you need to validate using other means, your crystallographic knowledge or some other external knowledge. And last but not least, because the ESDs are based on certain assumptions that are not fulfilled in kinematical approximation, the ESDs are not reliable and therefore we don't know the accuracy of the model. So the kinematical refinement is a good tool, but it has limitations. How can we deal with these limitations? We can try to average out the dynamical effects. I mentioned it already, combining, merging several data sets helps a lot, not only because of better completeness, but also because the dynamical effects that tend to be somewhat, they're not really random, but they tend to be somewhat random. So by averaging a lot of data, we can get data that are less sensitive to dynamical effects. However, the averaging does not remove the effects completely, no matter how much data you average. Even if you average infinite number of crystal data and at all orientations, the result will not, it is not asymptotically kinematical. Nevertheless, you can get very nice data. This is an example of a structure solved from data combined from 202 crystals, quite a lot, but the structure is very nice, including hydrogen atoms. And of course, you can get nice results with less than 200 crystals. There are approximate corrections. I will, for the sake of keeping the time, I will not go into details. I just mentioned that there is a correction for dynamical effects in X-ray diffraction. It's called extinction correction, because even in X-ray diffraction, there are some very weak, but some dynamical effects. And so it's possible to use this correction also for electron diffraction, but because that this correction is, say, semi-empirical and intended for only small dynamical effects, its effect or its power for electron diffraction is only limited, and but often it works. So it's a good tool to use if needed. There is also a publication on another statistical dynamical correction. I haven't seen it in action very often though. So as far as I understand, it's not available in any standard or commonly used structure refinement program. And finally, the final option is, of course, taking the dynamical effects account. Don't ignore them, just admit they are there and do the calculations of intensities with the dynamical effects taken into account. This is called dynamical refinement in short. And in the remaining few minutes, I want to say a few words about the dynamical refinement. Dynamical refinement is there is nothing really mysterious about it and nothing really complicated, because apart from the concepts related to the calculation of intensities, the dynamical refinement is just the same as any other refinement, as a kinematical refinement. But the principle is the same. You have observed intensities, you have calculated intensities, and you are trying to match these two as closely as possible by modifying the the parameters of the structure model, and in case of dynamical refinement, by modifying a few other parameters that are related to the calculation of dynamical intensities. So these special aspects to consider is that the crystal orientation needs to be taken into account when calculating dynamical intensities, and therefore symmetry-related intensities are not the same. Even if their structure factors are the same, their intensities depend on the crystal orientation, and two symmetry-related intensities are typically collected under different crystal orientation, and their intensities will therefore be different. So no merging, everything is refined against unmerged intensities. An interesting, not really fundamental, but important consequence is that the R factors are higher than for unmerged data than if you merge the data. Simply because if you merge the data, you already average out a bit of the noise. So the R factors are then nicer. And here in this screen, you see the difference. The right column, R ops are all, and weighted are all, are numbers that were obtained on one particular structure refinement. So the R ops is 4.54%. But if you calculate the R ops on merged data, so if you do a symmetry averaging, you get an R factor that is essentially exactly 1% lower. So it's, of course, it doesn't change anything about the result. It is just good to know that when comparing the R values and other statistics between kinematical and dynamical refinement. What's more important is that intensities depend on the thickness. And so thickness is a refinable parameter. You refine how thick the crystal is inside or during the refinement. And there might be even variable thickness considered, so you can have models for a crystal that it has a form of cylinder or a wedge or a sphere. And last point, the frame scaling that we are used to from data processing is not usable for dynamical refinement, because the frame scaling assumes kinematical diffraction, assumes equivalence of symmetry-related reflections, but that is not true for dynamical case. So the frame scaling from the data processing programs cannot be used, and the scales need to be refined separately for each diffraction pattern or a small group of diffraction patterns. This is a plot of such refinement of scales. See, it goes from, it's an arbitrary number, 1,200, goes up to 2,000, and then down again. That's a typical curve that occurs because of the smaller size of the crystal at higher tilts. So if you have a crystal that has a form of plate, if you tilt it 70 degrees, its projected size will be smaller. So the number of electrons that hit the crystal is smaller, and therefore the scale is smaller. So currently there are two programs that can do dynamical refinement on 3D data. For a long time it was only YANA 2020, but now since maybe last year more or less, OLEX2 also contains this option, which may be different in details, but it uses basically the same or very similar philosophy and ideas in the dynamical refinement. So this is just a sketch of the basic procedure. Just very quickly, you import the data from produced either by PETS2 or by Chrysalis Pro or by Dials. As far as I know, these are the three programs that can produce data for dynamical refinement. Import it, set up a few parameters that define the calculation of the intensities, and then optimize the thickness, the starting thickness, to get a good starting point for the refinement, and then just run a standard least squares refinement, just like with kinematical approach. And this nice dog here is here because the utility that calculates the dynamical intensities in YANA, it's called Dingo with Y, not I. So YANA is using an external program that is doing the calculations in an optimized way. So what the dynamical refinement offers is, compared to the kinematical refinement, better R factors, more accurate structure models, cleaner difference map, better position of hydrogen atoms, and very importantly, absolute structure determination. And I see that I'm running out of time, so I will not dwell too much on these points, and I will just show you a few examples of what the dynamical refinement is good for. I hope I will make it in the remaining few minutes. Okay, so these are some comparisons of the R factors, kinematical versus dynamical. Roughly, there is an improvement of about a factor of 2 between the kinematical and dynamical R factors. This is a nice example I like to show. This is a uranium containing phosphate, calcium, uranium, and it contains OH groups. And when everything is properly done, the R factor is about 4%, and there is a nicely visible maximum corresponding to the hydrogen atom on an OH group just next to uranium. So we can see even these subtle details in electron diffraction data. We can do even charge density refinement. These are just, again, 3 quick examples. Natrolite, that's a natural zeolite, quartz, silicon oxide, and tyrosine, of course, an organic molecule. And with accurate enough data and with careful dynamical treatment, it's possible to do charge density level calculations. And here you see the R factors. So if everything works fine, we can really get to R factors that are perfectly comparable with values that are obtained in X-ray diffraction. And finally, a very important aspect is absolute structure. In purely kinematical approximation, it is not possible to distinguish the 2 enantiomorphs. So 2 non-central symmetric structure models which are related by inversion center. In X-rays, this helps, so the effect that helps to distinguish these the 2 enantiomorphs is anomalous scattering or resonance scattering, which is very weak, and that's why it's difficult to determine absolute structure, especially for all light atoms. In electrons, it's the dynamical diffraction that breaks Friedel's law, and this effect is actually very strong. So you see, this is a plot of intensities for one and the other enantiomorph, and you can see that the scatter around the perfect line, which if everything was on a perfect line, there would be no difference between the 2 models. But we see that there is a large scatter of intensities differences. So electrons are very sensitive to absolute structure, even for all light atom structures. So this is an example of a co-crystal of empagliflozine L-proline, and there were 10 crystals analyzed, and only simply from seeing the R factor difference, it is easily determined which of the 2 enantiomorphs is actually the right one. There is also a statistical way of evaluating the confidence level of the correct determination of the absolute structure, and we can see that the combined confidence level is at a level of 17 sigma, which is really a large number. This is yet another case. This is really all light atoms. It's a cyclic peptide, and again, it was really easy to determine the absolute structure of this natural product. So I think this is an aspect that, well, it requires dynamical refinement. Kinematical refinement does not provide that information, but this is something that makes electron diffraction competitive with X-ray diffraction, even if small crystal is not or even if getting large crystal is not really a problem, because for poorly diffracting materials, it might be difficult to get the absolute structure from X-ray diffraction, but it is usually very easy and straightforward to get it from electrons. This slide shows the computing time. Just one sentence. Dynamical refinement can be time consuming, but nowadays with not too large structures, it's not a matter of hours, it's rather a matter of minutes instead of seconds for kinematical refinement. So it's definitely not something that is preventing anybody from trying and getting the structures refined. Here you see in real time the refinement for various settings of dynamical refinement. I'm afraid I have to skip this part, I'm sorry. So I wanted to say a few words about imperfect crystals, but I'll skip that and I skip to the summary to say that I showed you the procedure. The data processing is very similar to established X-ray procedures with just a few specifics remaining. And but electron diffraction is dynamical, and we need to be aware of that problem and either accept kinematical refinement with its limitations or do a dynamical refinement to get a more accurate results. I apologize for running a bit over the time, but if there is a little bit of, well, I thank you for your attention, and if there is a little bit of time, I'm happy to take questions.
Gerald, do you hear me?
Yeah, I can hear you. Can you hear me?
Yes, we can. Can you share your screen?
Yeah.
Also, while you're setting up, did you first hear MicroED or 3D ED? How did you get into the field?
I first heard it as 3D ED. So I studied at the University of Limerick in Ireland. So under Andy Stewart. So in Europe, we call it 3D ED.
Okay, take it away.
Sorry, 1 second. I'm just getting a little bit confused. Okay. Okay, so my name is Gearóid. I'm an application scientist at Quantum Detectors. First, I'd like to thank the organizers of this event for the opportunity for Quantum Detectors and myself to speak. Today, my talk is titled Advances in Electron Diffraction and Microscopy with Merlin. And the overall goal of this talk is to give you some insights into how the Merlin has been used in different applications in electron diffraction and microscopy, specifically with a focus on microelectron diffraction and 4D STEM. So normally with a talk like this, I'd start by going into some detail about how the Merlin works, but in the interest of time, I'll skip it and just focus on a couple of key points. So the Merlin is a hybrid pixel direct electron detector based on the MEDIPIX-3 technology from CERN. A single sensor has 256 by 256 pixels, but what we can actually do is we can tile individual sensors together to achieve larger detectors. So for example, we can have a 512 by 512 detector, which is much more appropriate than a single sensor for small molecule electron crystallography. The MEDIPIX-3 sensors also offer noiseless readout, which of course provides high quality data for a number of different applications, including electron crystallography and 4D STEM. And then these detectors are also radiation hard for electrons up to 300 keV, which means that we can obtain diffraction data from intense high energy electron beams indefinitely without the need for a beam stop. And one thing that's often overlooked is that this detector also has an open communication platform. So it's easy to communicate with the detector using something called a transmission control protocol / internet protocol. So this allows you to sort of integrate the detector into different workflows. So with that out of the way, what are the actual applications of Merlin? Well, a single sensor is very good for 4D STEM. So you can perform techniques like virtual imaging, magnetic domain mapping, orientation phase mapping, tachographic imaging, and the actual properties of the Merlin, its dynamic range, its speed, and radiation hardness make it also very good for different applications in the microscope, especially if you have the right tiling. So techniques like electron energy loss spectroscopy, and of course, electron crystallography. So today I'll briefly cover orientation, phase mapping, and also crystallography. So first, electron crystallography. I won't actually cover these because Partha did a nice job already explaining both microelectron diffraction and serial electron diffraction. So this will give me a bit more time to talk about some of the other things. What I will spend a bit more time on today is 4D STEM, perhaps because maybe maybe the audience isn't as familiar with this technique as they are with microelectron diffraction. And to explain 4D STEM, I'll first cover conventional STEM. In a conventional STEM experiment, you have a converged electron beam that scans the sample, typically in a raster pattern, so a pattern that looks like this. And then below the specimen, you have these annular or bright field detectors that collect electrons scattered through specific scattering angles. And then these detectors integrate the scattered signal into a single value. And then you have software that displays that intensity value in sync with the scan pattern. So what you're left with is these two-dimensional images. And the contrast of these two-dimensional images, of course, depends on the detector that you use to collect the electrons. So for example, if you had a detector configured to collect electrons scattered through high angles, namely a Hadoff detector, so high angle annular dark field detector, you'd obtain these Z contrast images. So these detectors are good for imaging heavier atoms. And you can see that just by the contrast. This is a gold nanoparticle on a carbon support substrate. But then this is an image obtained with a bright field detector, and these are much better for imaging light atoms. And you can see this is the same sample, just the contrast of the carbon support is much more clear. And so these detectors are good for providing this information. This is particularly useful for material scientists at very high frame rates, so megahertz frame rates. But this real-time integration causes a loss of information in diffraction, or momentum space as it's sometimes known. And so this loss of information sort of prompts the question, can we get more out of STEM? And the answer is that we can. If we add a pixelated detector to our column, we can, instead of performing real-time integration, we can obtain the full distribution of electrons at each probe position. So what we're left with is we're left with a four-dimensional data set. It's 4 dimensions because you have a 2-dimensional scan grid, and then at each point in the scan grid, you have a 2-dimensional diffraction pattern. So these data sets can go from megabytes to tens of gigabytes in size, depending on the acquisition parameters. So things like the number of scan points in the region of interest, but also the properties of your detector. So the number of pixels and the bit depth of the detector as well. So now that you've collected this data, which can again go up to gigabytes in size, what are the actual advantages? Well, one of the things that you can do is you can perform virtual STEM imaging in post-processing. So with virtual STEM imaging, you can obtain images that are very similar, albeit usually better than the images that you can obtain with physical Hadoff or bright field detector. But the power of 4D STEM here is that you can arbitrarily choose the number, shape, and even actually the operation that you applied to these virtual detectors. So you're no longer limited by the physical number and position of these detectors in your column. But I will say that virtual STEM imaging is sort of the simplest way of processing your data. And if you were only interested in virtual imaging, it's probably not worth getting one of these pixelated cameras for this application. But really, with 4D STEM, you have a wealth of information in your data sets, and you can exploit these data sets to perform new techniques, to obtain new insights into your materials. So for example, you can perform orientation, phase, and strain mapping, tachographic imaging, and electric and magnetic field mapping. So now that I've covered, well, at least other presenters have covered microelectron diffraction, and I've covered 4D STEM, at least briefly. The reason I've done that is because I wanted to talk about this case study where researchers in Cambridge combined or used microelectron diffraction and 4D STEM as complementary acquisition modalities. And I think at least it's probably fair to say that, as researchers, we are interested in, collectively understanding our samples completely. And microelectron diffraction and 4D STEM are just two ways of characterizing our samples. So Helen Lung, a PhD student, in collaboration, of course, with her group, specifically her supervisor, Professor Paul Midgley, and then researchers in GSK, a pharmaceutical company in the United Kingdom. They performed this work, Helen actually already presented at a webinar hosted by Quantum Detectors in March. So if you really want to learn about her work in a bit more detail, there's this webinar is on YouTube to watch. But I will cover it very briefly here today. So what she was doing is she was looking at obtaining a structure solution for xanthine nanoparticles. These xanthine nanoparticles are layered crystals, and in these layered crystals, you can have stacking variations, which can lead to things like twinning, planar disorder, and polytypism. And this, these things can lead to novel properties. And of course, especially for pharmaceuticals, you want to know if these properties are harmful or beneficial. So she went about obtaining a structure of these xanthine nanocrystals. In this case, she used a C to D. Actually, on this microscope, she did mention she had a Merlin detector, but it was a single chip detector, which wasn't quite big enough for these for the unit cell of these xanthine nanocrystals. Nevertheless, she obtained these incomplete microelectron diffraction data sets that exhibited multiple reciprocal lattices. She used reciprocal space sectioning to identify symmetry, and eventually she was able to determine that these xanthine nanocrystals exhibit twins, and some of these twins actually have a novel form. And you can see here in this image the two different forms in A and C, and then in B and D you can see in each of the layers the intramolecular bonding is actually the same, which is of course characteristic of these layered crystals, where the difference in forms arises again from the stacking variations. So one thing that she noted when performing this reciprocal space sectioning is the streaking in reciprocal space. And this, is characteristic of planar disorder. And so she wanted to understand the structure of these nanocrystals at a higher resolution. And so she turned to scanning electron diffraction. And this is, just another sort of form of 4D STEM, except instead of using a converged electron beam such that you get C-bit disks, instead you use a quasi-parallel nanobeam that still scans the sample. So you're left with a 4-dimensional data set, but instead you have these sharp reflections. You measure these sharp reflections, very similar to a selected area electron diffraction pattern, or those obtained with serial electron diffraction. Here is an image from her paper. You can see actually a schematic of the intensities in the data. You have here streaking, an elongated reflection, which is characteristic of stacking faults in the nanocrystal. And then in B, we have this virtual Hadouf image. Remember, each of these pixels actually has an associated diffraction pattern with it. These colored rectangles correspond to regions from which position average diffraction patterns are obtained. And then these are those position average diffraction patterns. And then what she did is she applied a number of different virtual objective apertures to her data set to generate these virtual dark field images. And so what I'm trying to show here is that, first she obtained these microelectron diffraction data sets, which gave her this average crystal structure. And what I didn't talk about is this orientation relationship of the twins. And then she applied scanning electron diffraction to these nanocrystals, which give insights into the domain distribution, the interface orientation, and also the local disorder. And you can see that just by even qualitatively looking at these diffraction patterns, you can see that the intensities changed quite dramatically as a function of position. And of course, these virtual dark field images highlight different domains that contribute to scattering in these scattering directions. One thing then as well is that, again, microelectron diffraction gives you these average crystal structures, which of course you get a structure file. And oftentimes in these scanning electron diffraction experiments, especially with material science, researchers often take a known structure file and then they generate a bank of diffraction patterns as a function of orientation and phase. And then they use these, they compare these to the experimentally observed diffraction patterns and assign phase and orientation to these experimental diffraction patterns. So really, microelectron diffraction can inform these scanning electron diffraction workflows. So Helen really nicely showed, I think, with her work that it's possible to, use information obtained with 4D STEM and microelectron diffraction separately. But, is it possible to combine 4D STEM and microelectron diffraction in in one experiment? And the answer is that it's possible, for sure. Researchers in Belgium at EMAT, they wrote this software called EMAT, they wrote the software called Eventem, which takes advantage of the user-friendly API of ScanEngine, which is a product from Quantum Detectors. It's a scan generator, so it allows advanced control of the scan cause on a microscope, and of course the Merlin detector, to perform these 4D STEM tomography experiments. And I'll just play this video. You can see what they're doing here is you take this scanning electron diffraction data set or 4D STEM data set as a function of goniometer tilt. So this is quite powerful because you can obtain data from multiple crystals, and then you can generate in post-processing these virtual microelectron diffraction data sets using these virtual selected area apertures. So again, each of these pixels here has an associated diffraction pattern, and so you can obtain these position average diffraction patterns as a function of goniometer tilt. And so you can precisely choose which pixels contribute to the virtual microelectron diffraction patterns. And this can offer improved signal to noise because you reduce the contributions from the background support, and it can also address the overlapping crystal problem. So I was actually initially going to end here, but what I wanted to do is I wanted to show some data that we recently collected using Merlin T4. So this is our latest detector. It's based on the TypeX4 ASIC from CERN. It's both an event and frame-based detector, which I won't be able to go into the details of why that's important, but effectively it allows for ultra-fast microelectron diffraction. And this data that I'm going to show you was collected at the Rosalind Franklin Institute in the United Kingdom. We worked on biotin crystals with a tilt range of 100 degrees at room temperature, 200 keV beam, and 0.4 electrons per angstrom squared. And the data was collected in 12 seconds. So the entire data set was collected in 12 seconds. And we achieved a resolution of approximately 0.85 angstroms. You see, this is a video of the data. It's not really sped up. I actually just trimmed a few of the frames at the beginning and at the end, just because you have some acceleration of the goniometer, which can lead to some issues in the data processing. But in these experiments, we're effectively at the limit of the goniometer, and so the detector is not really a limiting factor anymore, if it ever was. And so Merlin, what I'm trying to get at here is that Merlin T4 potentially paves the way for solving novel beam-sensitive structures because of its speed. So this is a video of the structure. I think there's the R factors are 20%. I think there's a little bit more work to do with refining it. I think I was a little bit rusty when trying to work on it. But thank you for your attention. If you want to contact me or reach out, this is my email. And Quantum Detectors also has a US representative. He's actually, I think, in the room there. His name is Donald, and you can reach him here at this email address.
Fernando, if you want to come, we can get this. For the sake of time, we'll wind down, but Donald is in the room, and you can meet him during the breaks and ask any questions. So Donald, where can you find a Merlin detector?
What's that?
Where can you find a Merlin detector?
Downstairs.
Downstairs on Trios 4. Great, thank you. Okay, so next up we have Fernando from Gatan, and it's actually going to be a double feature. You'll see him today, you'll see him tomorrow. He's going to do a demo on one of the detectors, another one of the detectors that we have downstairs. So Fernando, did you hear MicroED, another name first? And how did you get into this particular field?
Yeah, that's a great question. So I heard MicroED first, but I'm in California, not too far the Tamir's group, so I feel like that's his area. But to be honest, I come from a material science background, and when I learned about what MicroED was, I was like, what's different from just diffraction tomography? I found it a confusing term. And I think in general, like material scientists, bio people speak two different languages about the same technique of electron microscopy. So if I were to get on my soapbox, I would say that I think we all need to learn how to speak more of the same language with the same vernacular, because I found it very confusing, as as I already said. But to get started, I'm going to be talking today about how we can acquire MicroED data in an automated method using the Latitude D software based on our DigitalMicrograph platform that's downstairs. And specifically in relation to the context of our direct detection camera, one of them called the Alpine Vista camera, which is sort of installed on the same microscope. So as I was saying, I understood MicroED just to be a sort of diffraction tomography experiment. That's how my simple brain works. And so I won't spend any more time on talking about that. We've also talked about what is the MicroED workflow in general. It's very complicated. I've actually never done it myself all the way through, but I'm sure many of you here have or will soon. And sometimes people ask, where is Gatan supporting the kind in the workflow for doing MicroED data acquisition from start to finish? And really, Gatan, as is the topic of this discussion, it helps with the screening, the data collection from the microscope control point of view, and then also from the data acquisition point of view. So if you have questions about how you do the reconstruction and everything, I suggest you speak to one of the many other great speakers that have already presented today, and not myself. But as we all sort of may have figured out or have done by now experimentally, collecting MicroED can be pretty annoying because you have to manually, at its most basic, hunt around and figure out where the good areas of the sample you want are, and then go and actually set the centric height on the microscope, capture the images, and do this over and over and over. And so something that I think material science does terribly is that we're happy to use this manual sort of method for a very long time. And biologists were like, no, we need everything automated, and I agree. So having an automated solution to not have to manually adjust the microscope and the stage position, everything would be great. And so instead of getting stuck in this recursive loop and then having to learn how to use all the different softwares together, if you are familiar with DigitalMicrograph, which many people are, because many people are familiar with Gatan and the detectors because we've been around for a long time, we can simplify that using Latitude D by essentially capturing an atlas of your grid very quickly, similar to the RCSB platform that was shown earlier that's built on, I think, Serial M is what they were saying. You can identify multiple crystals at the same time, and then the software can control the microscope to navigate to all of those positions independently, and then control the camera to acquire that data relatively easily. So the general suite of this kind of automated data acquisition is called Latitude D, Latitude. For MicroED, we have the Latitude D version, which is the diffraction tomography. There's also a version that is used for doing single particle imaging. That's Latitude S, and then imaging tomography, which is Latitude T. So there's all sorts of things you can do within DigitalMicrograph. And I won't talk too much about more in the slides because we'll have a demo tomorrow, as we were saying. But the idea, as I was saying, is you can go around, find different crystal regions, assess them for whether or not they have a lot of diffraction patterns or not, and only collect full tilt series data sets from the crystallites that you do have. So this is a quick video of what that workflow looks like. We're looking at the DigitalMicrograph 3 software, if you've ever looked at it, but essentially on the left, we have this atlas image, which is our images of our whole grid, and then we can zoom in on individual grid squares, capture images of those grid squares, and then zoom in even further from to look at different particles, take a screening single diffraction image, and then a full tilt series if we like it. Something else I've learned today, if I look at these particles, these look like great particles to me. Material scientists see these kinds of things and are like, cool, I'm sure that'll be very good. Maybe even that looks a little too thick. But in this case, where MicroED is a totally different world from material science. So that's the data acquisition part. But the other thing that's important, as a lot of people have already talked about, is the detector that we're using. And so I like to think about it in terms of what is the actual data that we're acquiring look like, and how does that determine what we need from our detector. So these are two different kinds of regimes, essentially, of diffraction between proteins and small molecules. And if we look at the differences in diffraction patterns and think about what it is that we need to resolve with our detector to do our MicroED experiment, one of the things we need to do is have the ability to capture both a weak diffraction spot under low dose conditions, so we don't need a destroyer sample. So we need a detector with very high signal to noise that's also sensitive. We need to quickly acquire these diffraction images to have a high throughput. So you need a high frame rate detector. You want to be able to capture both intense spots and weak spots at the same time without saturating any of the spots. So you have the relative intensities or absolute intensities. So you need a detector with high dynamic range. And then you also need to capture, in some cases, very small spots or very small features in an image over a very large area of the diffraction space. And so that determines essentially how wide the field of view of your detector needs to be and how many number of pixels you need to have in order to be able to resolve all those features well. So here, for tomorrow's demo, we're going to be working with the Alpine Vista camera. We also have the K3 camera, which is a very similar kind of direct detection camera on other kinds of microscopes that they have here. Something that's special about the Alpine Vista is its ability to work at lower accelerating voltages than you may expect for a direct detection camera. So the Alpine really works well from 80 to 200 kV, whereas other direct detection cameras work normally at 200 or 300 kV. And if you're not quite sure what a direct detection camera is, this is a very quick diagram. Essentially, it means that we're directly detecting the electrons with the sensor and then turning that signal into a digital signal that we can read into the camera. We're skipping these first two steps, for example, of that are normally found in a simulator-based camera, where you actually need to convert electrons to light and then move that light and then turn that light into electrons and then into a charge. So a direct detection cameras, because you don't have this very lossy conversion process, are much more sensitive cameras in general. And then when you combine direct detection with counting, which is what we do here at Gatan and many other folks who make detectors do, you get an even better improvement in the data quality. So by itself, this is what an image may look like on the camera. With counting, you'll see a very different image that's going on here. So what's happening is that as each electron hits the detector, it's depositing some amount of energy over some spatial distribution. In some cases, it may deposit energy over many different pixels in your camera. And so you can have image processing on the chip that can identify exactly how much energy is deposited on which pixel and use that to reduce this energy, spatially distributed level of energy to a single pixel and a single event, and that's what's called counting. So on the left-hand side here of the image I showed previously, you have a couple of different sources of noise. For example, you might have a variable amount of energy that's deposited on the sensor by a single event, which makes some pixels look really bright, some maybe are less bright. You also have what's called read noise, which is something that every sensor has, which doesn't make the background black, but gray levels, which is not good because that affects your signal to noise. But when you do the counting, essentially you're able to remove these two sources of noise to your image, and that's what people usually are talking about when they say there's noiseless imaging, because they, with whatever counting algorithm or thresholding they've done, they're able to remove the read noise from the image. And so that improves your signal to noise on the camera. Now, something else that a lot of people in the cryo world are always interested in is the DQE, or the detected quantum efficiency, or how sensitive the camera is. And that's also, as you can see, the sensitivity depends on essentially the spatial frequency of the information that you're trying to detect, as well as the accelerating voltage that you're using in your experiment. So this is just showing some, specifically for the Alpine, how it's tuned to have its best sensitivity at lower accelerating voltages. So this is 200, and then at 100 kV, it really starts to shine, even over sort of our flagship K3 kind of camera, which is tuned for more 200 and 300 kV acquisition. So one of the benefits that you get out of diffraction when you're doing a MicroED experiment with a direct detection camera is sharpness of spots. So this diffraction pattern here is from a zeolite material. This image was collected with a simulator camera, and so we can take a line profile of these spots and see some spots visually and in the line profile. And when we look at the direct detection camera, we see much darker spots, much brighter spots, much better signal to noise. both visually at the pattern and then looking at the line plot here. So it's a really big improvement in your ability to detect small, faint spots in a diffraction pattern that can be extremely critical for your experiment. And as we talk about other aspects I mentioned, that we need high signal to noise, we need a high dynamic range. This is showing an example of what dynamic range is kind of possible. So we can look at, for example, the transmitted beam that has a huge amount of counts compared to many of the small diffraction spots that only have, less than 10 counts in this line profile here. So having a direct detection camera compared especially to a simulator-based camera, which is the more traditional type of imaging technology that you may have used as you were getting started, really delivers a lot of advantages of having higher, sharpness of your spots, higher throughput because of the frame rate, which is something that I haven't really talked about too much here. And the sensitivity allows you to explore a wider range of materials that are beam sensitive that you couldn't see with other types of cameras because of the lower sensitivity or any kind of dose limitation. So this is just a quick example that my colleague from Detectors already showed of doing MicroED on acetaminophen. You can get really nice results. This is actually from a hybrid pixel camera, which just brings me to my summary of my talk. The idea being that with direct detection, you can get really nice diffraction patterns for your MicroED experiments. We have the Latitude D software that lets you do the automation of the acquisition. But really, even though I've been focusing right now on direct detection, there's other types of cameras out there, like hybrid pixel, which Gatan also offers, I'll mention. But when you sit down to look at a material, you have to think about what's the speed I need, what's the dose sensitivity, am I looking at a lot of very sharp spots over a wide range in the diffraction space, because all of that affects essentially how pixelated you need your camera to be, how fast you need it to be, and what its noise and sensitivity properties you need it to be. So if you have any questions based on that, you want to talk more about what experiments you're doing, feel free to reach out to me later today or at my email, fernandocastro@ametek.com. So thank you.
When you're asked to design a perfect detector, and given that a TX multi first will, when you say high dynamic range, what are the electronic fluxes you're asked to accommodate?
Yeah, so that's a good question, and it's really hard. For example, in the bio world, low dose is 1 electron per pixel per second or lower. In the material science world, low dose is like 1,000 or 10,000. And that's one of the things we're just like talking totally different languages. So there is no perfect detector that exists. There's too many different parameters that you have to optimize and have trade-offs essentially across. And yeah, the huge orders of magnitude in terms of the kind of doses that people are using. Although it is getting closer and closer as people are interested in MOPs and battery materials, et cetera, et cetera.
So is it okay to crank the microscope down to spot 1 and use no beam stuff on my K3?
Good question. I wouldn't do that probably. If you're interested in relative intensities and intensity of diffraction spots, one of the things you have to think about is essentially what's called coincidence loss. And what that means is that the frame rate of the detector determines how many electrons we can count and do this counting process for. So if you saturate this counting algorithm, then you start getting coincidence loss. So maybe it sees 2 events happening very shortly in the same amount of time, and it says that's just 1 event, and that decreases the sensitivity of your detector. And so that optimal counting rate is detector dependent. And for the K3, it's, I think, something like 20 electrons per second. So if you wanted the most, spot 1 just blasting your sample, I would say then you should really just kind of start thinking about a hybrid pixel type camera, which are much better suited for those kinds of experiments, with the trade-off that they have much larger pixels, smaller amounts of pixels that affect what image resolution you can effectively. All right, thanks everyone.
Okay, welcome back, everyone. We have Chenghua coming from, I got this wrong in the schedule, so make sure you update. It's the RCSB PDB. Make sure you have both acronyms. For you, did you hear about MicroED or 3D ED first?
I heard MicroED first, but I would touch on that on my slide. I just added.
Okay,
So
let me know. Very good.
okay. First, I want to thank the organizers for inviting me. And talk about the community, and we appreciate so much they include us, PDB, as part of the community because not everyone see it that way. Some consider us like long-term storage box, and the only thing matter is the box number, which is the PDB ID, and the only difference is we don't charge a fee. So, having said that, so today I hope I can achieve two goals for my talk. First, for students to understand briefly the 3D ED or MicroED structures in the PDB and an overview of the definition and annotation process, validation as well. And also for the experts in this audience, I want to introduce the improved data model for the future definition and validation. First, a little bit about PDB. So you have heard that many times. So we are the first open access digital data resource since 1971. And it's the single global archive with now over 240,000 structures. And the yearly definition in 2025, this year, is approaching 20,000. So that's a lot. And I also want to read that many of these structures you see are from 3D GAN. It's a joint organization managed by the regional partner from RCSB PDB, which is us. We take care of the structures deposited in the Americas, and also the PDBE for Europe, and PDBJ and PDBC for Asian definitions. We also have a specialized center of the MPP, which for 3DM, of course, maps, and BMRP for MR structures. But all these PDB data are validated, deposited, and verified using the wwPDB one-depth system, which is the one we're going to improve. So for PDB, we knew 2D electron crystallography first, and before anything about MicroED 3D ED. In 1990, the first PDB structures resolved by 2D electron crystallography on bacterial dopsin was resolved by 3.5 angstrom. That was membrane protein, and it can crystallize in a 2D form or special molecules. But in the next more than 20 years, you see only like a few structures resolved per year. And in all this year, there are about less than 30 structures. Because to use this, you have to have very special molecule. So it's by the nature of the molecule, not by the technique. But then we come to the 3D ED and MicroED in 2017. That was the first structure resolved on lysozyme. In the past 10 years, as you can see here, the MicroED or 3D ED kind of boom. For this year, by October, there are 52 depositions already, which is a record. And so far, there are about 300 structures resolved by electron diffraction in the PDB, and about 20% from 2D, most from early days, and 80% 3D MicroED, most here. Here, we just want to show some examples of the structures in the PDB resolved by electron diffraction. And it's a distribution by molecular weight in terms of dalton. And then from the very low end, you see a huge peak of small peptide about like around 1K. And they can be resolved at a resolution up to 0.6 angstrom. And you see another peak here, lysozyme at 15K, which is a modular system for method development. There's another peak here for proteinase K, also pretty much similar to isotype. And up here, you see the bigger molecules at 50K resolved by MicroED about 2023. And on the far end, which is high molecular weight molecules, most of them are resolved by 2D electron crystallography in the early days. Then what about the electron diffraction data and structure quality in comparison to the X-rays? Here's a histogram of resolution of all these electron diffraction structures, and the median is 1, which is almost exact the median of X-ray structures. Although you do see some low resolution structures, most of them are from 2D EC. And in terms of the model, the R3 is indeed a little bit in the percent or greater than the median of X-ray structures. We also see some other statistics such as the data completeness, which is a little bit lower for electron diffraction, which is understandable since you do this rotation with a limitation. So if you have resolved 3D or MicroED data, and we are at very downstream, we're in this community to help you deposit and validate these structures. If you consider that the upstream that you collect data through, the center here with the support from NYSBC, and also in the middle, like the processing the data and do the structure solution refinements with help from the software community. And we are at work end where your structure will join this the ocean of the thousands of structures. And we want to make sure that your structure is complete and properly marked for all the features so people can find your structure and it can maximize its impact. To start a MicroED or 3D deposition, you have to choose a method first. And so far, everything is under the envelope of electron crystallography, which includes both the 2D EC and 3D MicroED. And here you will see questions that not very meaningful. It said, are you depositing coordinates with this definition, which is nonsense, because as far as now, for every 3D MicroED structure, there is coordinates modeling. The reason is we were using 3D EM framework. That is not kind of very good fit, which is why in the later section we'll talk about the improvement. And also it asks about whether you want to deposit associated map. But as we know, the maps from the 3D MicroED are usually calculated, recalculated from diffraction data. So, but it is what it is now, and you can choose among these options. And once you choose that, you'll be asked to upload files first. And if you have chosen just depositing the structure factor, you will just request a PDB ID only. If you have chosen to deposit the map as well, actually you will get the MPP session. So for the one on the left, with structure factor only, you only need to deposit the model coordinates and the SF file. It can be MTZ file, MMC format, or MMC file. And if you deposit map, it asks you to deposit the map in the this MRC64 format and provide this information that also may not be very relevant in 3D MicroED. But again, it is what it is now, and it will change. So after that file upload, you'll be asked to provide other information. And if your file already has the information here, it will be parsed. For example, the high resolution, low resolution, etc., data completeness. But you also see cases where there's experimental information about microscope, which makes sense, but image recording. And you may be asked for example, defocus value, which also makes no sense. So, which is why this is the current framework, but we want to improve on that. Every PDB structure deposited goes through the validation process. And PDB is our type of experimental data, which include both atomic coordinates model and experimental data. Of course, for different methods, there are different experimental data. For MX, we spend macromolecular crystallography, their diffraction data. For 3DM, there are maps, half maps, etc. For MR, there's chemical shift restraints. So first, the geometry of the molecule is checked against the established chemical reference in terms of bond lengths, bond angles, etc. And they also check the experimental data quality itself. We get an armory for diffraction data. And there's good initial fit between atomic coordinates and method-specific experimental data. Of course, this will be method-dependent validation. And different from the small molecule structure, for PDB, there could be a structure with millions of atoms. And there's this concept of global versus local, because you want to know how good the structure is overall, and also for some structures, you want to know the specific section that, for example, where ligand bonds the molecule, how is that ligand binding site? And so they both need to be validated in a separate way. And coming to that again, there is validation for different molecule components for polymer, ligands, carbohydrate, etc. They will be validated based on their chemical properties. The authors can do validation through different processes. Before they deposit, they can do pre-deposition validation, either through an interface of server or through an API by programmatic access, and which generate preliminary report for the author to review, to preview. And when an author start application, the preliminary report is also generated. But only when the authors click submit. When we receive structures, we have a team, dedicated team with experts from different fields to review the structure, sometimes manually, and then generate the official report. This is a report associated with the manuscript submission for some journals. And when the structure is eventually released, this report will also be released together with the model and experimental data. And for journal review, usually we generally report to the author, and you're going to provide that report to the journals, and then journal transfer this report to the referee. In terms of the general chemical geometry analysis, the polymers, which are usually proteins and nucleic acid, analyzed for the following geometry issues, for example, bond lengths, angles, atomic classes, from a change outliers, section, Rotman outliers, etc. To analyze for by mole property and some PDB in-house software. And the report will report on, for example, standard geometry, those contact port angles, and it will also generate residual specific plots. The reference are included here for the geometry validation. I'm sorry, I think we get past that. 95% of PDB users are not structural biologists. So for those users, we need to provide a generic metric for them to review the quality instead of looking at each specific structure feature. So we generated this slider, which compare this specific structure to the other structure in the PDB. Either all of, this solid box is the relative percentile against all structures, and this empty box indicates the percentile relative to this specific method. And in this case, you can see this is percentile against EM structure, which is not actually right for 3D MicroED structures, which we are going to change. And also there's this residual specific plot for general users where it highlights the quality by numbers. Green means good, yellow means some problem, and orange means more problems. The gray area means this is specific PDB is that some of the polymer residues are in the structure in the crystal, but not observed because they were disordered, either because they were looping or they were flexible loop or because the density is weak. And the red diamond indicating where the fitting between the model and the electron density map. In this case, it's electron static density map is now very good. Beacon is a specific feature in the PDB because they are usually associated with the larger proteins. So it's a binding site, and binding mode is more important. And many of these ligands are the research focus. So we validate them specifically. And the validation is not against the other PDB structures because they are all like low, kind of relatively low resolution compared to the CSC. So we compare them to the Cambridge structure database of small molecule structures as a reference. And for example, there are bond length distribution for specific bond. And we calculate RMIC, and if Z4 is greater than 2, it's considered outlier. Same thing for the bond angle. There are other the analysis also include parity, torsion angle, ring, etc. And here the example of NDP. NDP is NDP, which is dinucleotide includes nicotine and adenine. And it has specific indicator because in PDB structure usually there are multiple instances, and this is one specific instance. It has bond length, RMSC, overall quality of 0.71, which is okay, but there's one outlier. Same thing for the bond angle, and the specific bond outlier, this bond, the observed value, the ideal value is observed in the CST and Z4. And also there's graphic depiction, which use different colors on this chemical drawing. And green means this bond is good, and magenta means the bond is a statistical outlier. And same thing for the angles, portions, and rings. Now we come to the global overview of this so fit between the experimental data and the structural model. This is just same, almost identical to X-rays, where you have resolution, you have diffraction data summary, and you have R and F, etc., which is very similar to the table 1 finding X-ray structure publication. Also, if we want to upload the map, it provided this overview between the map and model, where the ribbon representation of the atomic coordinates in blue and the electron density map in yellow. So I have indicated the problem with this the current deposition validation system. So we want to improve that. The first thing we did was to reach out to the community and seek feedbacks. So we consulted altogether 18 people, including 7 from US, 7 from Europe, and 4 from Japan, just to make sure we have a good representation of the entire world. And they include researchers, scientists, and software team leads. I think some of you, like Mike, was within this group. And we thank them very much for the feedback and their suggestions. And we also seek feedback from depositors and from others occasions, such as the meeting here last year. And data model and data have been sent and shared with all the stakeholders. So here's what they say. So first thing first, 3D ED versus MicroED. When we sent out the initial proposal, it was MicroED. Everything was MicroED. And we received pushback from that, from most European and Japanese scientists. So they claim like 3D ED is the standard term for this technique. And so what we do is we are going to use them both. And we're not going to make a choice. So everything here you see on my slide, if you don't see 3D MicroED, that's my problem. So I make sure it's a good representation of the entire community. So they really don't like us to focus on the map because the map is derivative. And several people say this map should automatically generate from the uploaded structure factor. MTZ means the structure factor MTZ. And only structure factor files should be used for validation. And do not ask for things like do not defocus, standing, etc. And you should have a proper differentiation between the 3D MicroED and 2D electron crystallography, because continuous rotation procedure is specific for 3D MicroED, and this information should be collected for this supplements. And the diffraction data process software should resemble that of actually, because essentially it's a subset of diffraction method. Last year, when I gave the talk here, this is what I did, because when we compared actually MicroED and 3DM, and we saw similarity and we saw differences. So-called data model is how we organize the metadata. If you have never seen, this is in the MMSIF concept, but if you have never seen MMSIF, imagine you consider that as JSON or XML, where you have attributes or key and values, and consider that a collection of attributes or key. And these are so-called group, MMSIF groups. And then actually use XPTL group to collect visualization information. Usually there's not much to do with the preparation of actual crystals. There's diffraction group describing the diffraction data collection, reflection group for data process, and then the final refinement, modeling refinement. And for MicroED, you see identical process for visualization, or almost identical for reflection, and very similar thing for refinement as well. However, the preparation actually crystals loading is kind of similar to how EM sample was prepared, and the diffraction data collection is somehow similar with actually, but there are differences. So we were thinking to build this dedicated group just for MicroED or 3DM. I'm sorry, here do miss the 3D. Okay. But this received pushback in the past year because experts said that you should maximize the usage of the existing metadata attributes with other methods, such as iTree, because it's a subset of diffraction method. So what we do is we have changed this now to this organization, which means we're going to resemble the metadata collection process as that of iTree. As you can see here, the preparation of iTree crystal for electron diffraction will be some update to existing XPTL group, and the diffraction group will be updated to include electron diffraction. And this is also in the context of that, the PORSIF is being updated with the ED extension for small molecules. Just summarize in terms of this major updates, which is for XPTL group, is for experimental description. We're going to add the subtype to differentiate between the 2DC and 3D MicroED. And we're going to add this crystal process to record microcrystal production, which is usually happens after crystallization process. And the good thing about this is this collection can also be used for BioXFAB. And for diffraction data collection metadata, we're going to update the diffraction measurement category to include IOSTR approved or 6ED extension, and add a dedicated category, metadata category to report 3D MicroED specifically. And for the zero ED you heard from the early talk, we're going to reuse the XFile group, although the name says XFile, but this group is generally designed for any zero diffraction data. And short time. So this is an example of a dictionary definition, and this is so-called MMSIF data items, which include the category name and attributes. Here, These attributes, this whole item report the starting end of a crystal rotation. We do continuous rotation. And there's rotation rate, etc. with dedicated unit. This is degree per second. And exposure time, etc. And for this item, that was borrowed from the IUCR electron diffraction signature system with specific indicated here, and borrowed the entire definition and enumeration from the IUCR courses, so that they are consistent. And this is just an example that you can see that this is a real PDB entry. They got starting angle starting on 0, angle ends at 20, and the rotation is of 0.05 degree per second. And of course, this is continuous rotation, etc. And there are some other examples of this is how microcrystal is produced, and with the method is FID mining. And this is instruments, and the minimal dimension is 0.3 nanometers. Unit is nanometer with 300. This is micrometer, and 0.3 means 300 nanometer. It's almost optimal size. And this is the example of dedicated data categories just for 3D electron diffraction, which means they're different from X-rays. For example, there is the fluence rate at 0.02 electrons per square angstrom, and there is total fluence accumulated at 0.84 angstroms electrons per square angstrom. That data model have been reviewed by several experts in the field, and will finish review by the end of this year, and will be implemented on that one-lab system in 2026 by me. So the definition interface will resemble those of X-rays under the macromolecular diffraction framework, which means SFI will be sufficient. There will be no map, and we will share the page with X-ray, neutron diffraction, etc. And there will be dedicated page for 3D record. And same thing for validation. We resemble that of X-rays. And we also want very support from other programs. For example, we're working with Phoenix team to make sure they understand our update and in the future to produce those data items. And I'm also the author of PDB track. We're going to introduce the process for 3D MicroED deposition, prepare, and log parsing, which means when you process data, you have a log, and you can just put things in the PDB track and parse it out for your deposition, just to simplify it. And with that, I will thank my colleagues, and this is our director, Dr. Stephen Merlin. We're supported by a joint grant from NSF, NIH, and DOE. And if you want to understand more about PDB, you can join this upcoming event. Usually, we're talking about structure. This is the integrated structures, and it's process resolved by multiple methods such as cross-linking, small molecule diffraction. Small angle diffraction. And there's also integration of the CSM, computed structure models, on the RCSB website, which someone can help you to understand how you can combine that to the experimental structure exploration. And we are going to retire the expo if we have ever used this. And we are also approaching the time that the 4-character PDB IDs are being used up, which means, by the end of 2028, the PDB ID will be 12 characters, will be PDB underscore with 8 specific characters. And we have other past webinars or courses where you can learn about PDB. They are all concentrated in the PDB 101 site. And having said that, I'll finish my presentation. Thank you very much.
Questions?
The question looks good.
Well, you do challenges in different communities. do you find it easier or harder to determine who the community is in different fields?
If I understand you properly, you mean to identify the proper stakeholders.
Right.
Right?
Because you're trying to
Yes.
your best to have all these events to get them to participate. And how do you know you're reaching the right audience?
So for each specific major methods, we have this working group. For example, there's I3 working group and including people from like Paul Adams. So they were like the community leaders in terms of software development and technique development. So they will periodically meet and provide guidance to us. And for very specific things, which is such as the thing we're doing now, I'm also involved in metalloprotein remediation. It's a mess. And I mean, I guess whoever's now understand the question, the complexity of the metallic compound, because there were just so many valency problems, coordination problems, for which we really have to stretch hard. We hire someone who's exactly from that community, so she knows who to contact with, and then those people can introduce us to the greater community. That's how we approach things.
Thank you.
Thank you.